Hi, my name is André, and I will be presenting to you this work entitled Sensitivity of the Brayton cycle efficiency and emission parameters to the recuperator effectiveness through a numerical model based on equilibrium constants. To begin, the Brayton cycle was developed by George Brayton in the 19th century for piston engines, but currently the most common use is the gas turbine that operates in an open cycle. The two main applications of the Brayton cycle are the jet engine and electric power generation. To put it succinctly, the bibliographical research focuses on two studies related to the Brayton cycle applied to space power generation and power generation for hypersonic vehicles. In the first case, thermodynamic modeling is designed with the recuperator characterized in terms of the effectiveness as a function of temperature. In the second case, the modeling is similar to that adopted in the present work, using isentropic efficiencies of the compressor and the turbine to determine states 2 and 4. In addition, the recuperator effectiveness is defined using enthalpies instead of temperature. The Brayton cycle is usually modeled by operating with air for all states. The objective of the present work is to evaluate the Brayton cycle with a recuperator and modeling the combustion process using chemical equilibrium to determine the composition of the combustion products. From this evaluation, the behavior of polluting gases and the thermal efficiency of the cycle are analyzed with respect to the variation in the effectiveness of the recuperator. Thus, this analysis allows us to balance the cycle efficiency and the emission of pollutants. Once the pollutants are determined, we compare the results to the CONAMA emission limits. Now, about the methodology. First, we take a look at the description of the Brayton cycle. The compressor admits fresh air at state 1 at the standard pressure, which is the lower isobaric line. The admitted air undergoes compression work, raising the fluid pressure to the operating pressure of the combustion chamber, which is the higher isobaric line. The compressed air at high pressure enters a combustion chamber, and the fuel is injected into the air. The reaction takes place at constant pressure. The exothermic reaction releases energy in the form of heat into the cycle. Then, the combustion gases at high temperature and pressure expand through several stages in the gas turbine, producing work. A fraction of the work is transmitted by the shafts to operate the compressor, and the remaining work is the net work output of the Brayton cycle. The exhaust gases leave the turbine at atmospheric pressure, being discharged to the atmosphere, configuring an open cycle. However, the outlet temperature of the gases in a simple Brayton cycle is well above ambient temperature, and as a result, the energy in the form of heat from the combustion products would be lost if the gases were discharged to the atmosphere. So, the recuperated Brayton cycle recuperates part of the energy that would be lost in the atmosphere in order to preheat the compressed air before it enters the combustion chamber, using a recuperator that is a countercurrent heat exchanger. The hot gases from the turbine exhaust line exchange heat with the cool air leaving the compressor in a heat exchanger, normally in parallel pipes flowing in opposite directions. The exhaust gases are cooled from state 4 to state 6, while the air leaving the compressor is heated from stage 2 to stage 5, before stage 3, as presented in figure 2b. At the end, the exhaust gases leave the recuperator entering the atmosphere at a lower temperature than T4 and at atmospheric pressure. The premises adopted in this work are steady state condition, the fluid velocity and head losses are not considered, the compressor and turbine are modeled as adiabatic, the reference values are atmospheric pressure and the initial temperature is 300 Kelvin. Standard air is defined as 21% oxygen and 79% nitrogen. The input data used to evaluate the gas cycle comes from Branco, as you can see in the table below. The methodology used to solve numerically the properties of combustion products is based on a method applied by Olikara and Barman, using equilibrium constant for gas phase combustion products of hydrocarbon fuels. The modeling of combustion reactions is done as described by Ferguson. The product species of importance resulting from dissociation are oxygen, hydrogen, OH, and NO. Therefore, it is necessary to consider 10 significant product species, where A sub S is the stoichiometric air-fuel ratio and phi is the fuel-air equivalence ratio. There is a need for 10 equations since there are 10 variables. From the principle of mass conservation, balancing the atoms generates 4 equations. And chemical equilibrium provides 6 additional equations. The equilibrium constants are obtained from the data in the Janef tables. The system of 10 nonlinear equations is implemented through Scilab using the fsolve function, with the initial required value as the stoichiometric solution, which increases the convergence of the algorithm. When the mole fractions are determined, the mixture composition is known, and the thermodynamic properties can be calculated. All states are determined following the logical sequence as presented in the algorithm, and mathematical modeling is detailed in the written work, and next, the results are discussed. The modeling of the Brayton cycle considering combustion and the recuperator is simulated for different effectiveness of the recuperator, being 0 for the case without recuperator, 0.4, 0.6, 0.8, and 1 for an ideal recuperator. The results for the thermal efficiency of the cycle, varying according to the various effectiveness of the recuperator, are shown in figure 3. When the recuperator is added, the thermal efficiency of the cycle rises since part of the energy that would be wasted is used to heat the compressed air. The square marker represents the result obtained by Ferro, using the same modeling considering combustion, but without the recuperator. An increase of almost 5% is noted for any effectiveness value of the recuperator above 40%. As you can see, the cycle thermal efficiency remains virtually constant for the evaluated ranges of effectiveness. The first equation refers to the thermal efficiency and sheds some light on this constant behavior. The addition of the recuperator does not modify the compression work, neither the mass flow rate of air and fuel, nor the chemical energy of the fuel. Therefore, the only variable is the work produced by the gas turbine, which is defined in the second equation. And the turbine isentropic efficiency is also constant. Thus, it is necessary to assess the enthalpy variations at stages 3 and 4. Figure 4 illustrates the enthalpy variations for each effectiveness of the recuperator, as well as temperature variations. The recuperator influences stage 3, and this effect is observed when enthalpy is calculated at stage 3, since there is a term in the energy balance dependent on stage 5. As the effectiveness of the recuperator increases, the rate of heat transfer to the air in the recuperator increases. So, the higher the effectiveness of the recuperator, the higher the temperature T5, and consequently T3 and T4 will be higher than before, and the temperature rise is nearly constant as it can be seen in figure 4a here. Enthalpies H3 and H4 are dependent on temperature and pressure, while H5 depends only on temperature because state 5 is only air. Therefore, even though the temperatures and the corresponding enthalpies rise by the presence of the recuperator, the thermal efficiency remains constant because the variation in enthalpies remains virtually constant, as you can see here. Due to the concern regarding environmental issues, another point that shall be mentioned is the pollutant emissions. Figure 5 shows us the concentration of CO and NO gases when they are discharged to the atmosphere at state 6. The CO concentration remains below 0.2% regardless of the effectiveness of the recuperator. The NO concentration is almost 0.5% for the lowest effectiveness, and it is reduced by 30% for the ideal case. Lastly, for the case without recuperator, the combustion products do not transfer heat to the air, and therefore the outlet temperature of the gases leaving the turbine is higher than T6, and the CO and NO emissions follow the same behavior. It is important to compare the CO and NO emissions to the maximum emission limits determined by the CONAMA. To draw the comparison, the effectiveness is kept fixed at 80% and the concentration of pollutants are illustrated in figure 6. The CO concentration for temperatures below 1300 Kelvin are less than 99% of the CONAMA's upper limit, and there is a considerable increase for temperatures above 1500 Kelvin, reaching the maximum limit at 1750 Kelvin. The NO emissions are higher and reach the concentration limit at 1080 Kelvin. As you can see here, the first vertical line. For the combustion gases temperature above 2000 Kelvin at state 6, which is the second vertical line, the concentrations are well above the allowed limits, as we can see here. For this reason as well, it is feasible to use a secondary recuperator to lower the outlet temperature and consequently reduce emissions to a secure level. Concluding, the present model suggests that there is a 5% increase to the Brayton cycle efficiency with the addition of a recuperator, regardless of its effectiveness if above 40%. The recuperator effectiveness demonstrated, nevertheless, great impact on the emissions control strategy. Also, according to the present model, a single recuperator is not enough to reduce the exhaust gases temperature and pollutant emission levels. Further treatment for the exhaust gases are necessary. Thank you.